All right, welcome everyone. I believe this is our last talk of the evening, and I'm pleased to welcome James Sochacki.
Very good. So
Oh,
Tova,
thank you.
that's actually how I used to tell my students when mathematicians had to use chalk. I told them my fingers were so chalky, exactly like
Yeah,
you said
it works. Yeah.
it.
Awesome. So take it away.
All right. So I'm going to tell you guys if you were at Ryan's talk, uh, Ryan and I have never met before, and you'll see why as I go through my talk, why I said that if you were at Ryan's talk. Okay, can everybody see my screen there? Hello?
Yep, it's good.
Okay,
Yeah.
good. All right. So Ryan talked about the golden ratio, and you can guess it's going to come up in this talk. So I'm going to talk about a simple mathematical idea that's been around for a long time that can help in a lot of differential equations modeling, especially in biology, chemistry, reactions, and some physics problems also, but mostly biology and chemistry reaction models. So Fibonacci came up with this idea of the golden ratio that Ryan showed was an answer to his differential equation. And I'm going to talk a little bit about how it comes up in nature and what it is. And Fibonacci, they're not sure when he was born and died, but they have an idea, just to give you a ballpark of when we're talking about when these ideas started. And now with computers, we could do a lot of stuff that Fibonacci couldn't do that we can now do. And then Pascal came up, his triangle was in the 1600s. And then Newton sort of came up with the differential equations idea, right? Sort of, him and others, but he did a lot of it. And you could see he intertwined with Pascal. And then I'm going to talk about Maclaurin, who intertwined with Newton some, and hopefully, if there's students in the room, they've seen Maclaurin's series or Maclaurin polynomials. And then Taylor also did work with polynomials and stuff. And actually, Cauchy once said that if it wasn't for Taylor, he wouldn't have been able to do all the mathematics he had done. So Taylor series and Taylor polynomials were quite important even back then. But now with computers, we could do a lot of things with Taylor and Maclaurin polynomials that are pretty neat. And I hope to show you that in this talk. So I'm going to talk about things in the literature that's called the power series method or automatic differentiation. And computers can do automatic differentiation pretty quickly. And some people call them differential transforms, but they're all three of these are the basic ideas that Taylor and Maclaurin did thanks to Newton. And I'm going to show you how it's related to what Pascal and Fibonacci did, which was more related to biology and chemistry, what those two did. And so my idea is just basically working with polynomials. And we, of course, to get as good an answer as possible, we usually try to let n go to infinity and then measure our error. But I'm not going to worry too much about letting n go to infinity. You can kind of think of n as your favorite natural number and sort of work through with what I'm doing. Any questions up to now? Okay, so if you like these ideas, me and my colleagues at JMU worked on these for a long time, and my students, just to show you how powerful this modeling is, my students used the ideas I talked about in this talk and built accurate models for the motions of the planets and the moons of Jupiter. And I kind of built a little LLC after I retired based on a lot of the ideas I'm going to show you. And you can go to my website. But right now I work a lot with universities and the government and doing research. And I work in the areas of teaching, education, research, and production. And there's a link here called PSM textbook. I'm not going to go to it, but it's a open access textbook, so I don't make any money off of it. My goal is just to get people to see that nature is based on Fibonacci and Pascal and power series. And there's a lot of neat stuff we can do with that. So most of the stuff I'm going to talk to you about is just simple algebra and calculus. Thanks, Tova. Simple calculus and algebra polynomials. And I'm going to base it, sorry, I hit too fast. So again, I showed you what x is, and I'm going to base it on the foundation polynomial that you first learned probably in high school, which is the geometric series, 1 plus t squared, and so on. And we could write that as a sequence of the coefficients. All we need in the computer is the sequence of coefficients, which are all ones. And we know from the geometric series that this guy looks like 1 over 1 minus t, as long as the absolute value of t is less than 1. And then, of course, you tell in calculus, you ask your students, can you take the derivative of a polynomial? And most of them love taking derivatives of polynomials. So they can take the derivative of that and look at the coefficients. So you go from all ones to counting, 1, 2, 3, 4, 5, right? So now you have this new sequence that's a little more interesting than the one before. And if you take the derivative of 1 over 1 minus t, you get 1 over 1 minus t squared. And again, for the absolute value of t less than 1. So what do you notice about x prime and x? What's the big relationship we see between x prime and x? Anybody?
I see
So
that x prime is equal to x squared.
very good. Thanks, Tova. So, right? So there's our kicker. X prime is equal to x squared. So that means if I square x, right? If I square x, I will get x prime. So the square of the polynomial, all whose coefficients are 1, is the polynomial whose coefficients are the natural numbers in the counting order, right? And so we get that. So we could say that if we square the sequence of all ones, we get the sequence of counting numbers, which is pretty neat. All right, so if you're Taylor or Maclaurin, what do? You take the derivative again, right? So you take the derivative again, and you get 2 plus 3 times 2, and so on, just taking the derivative of that polynomial, which is what we do when we teach Maclaurin series and Taylor series, right? And so we look at the coefficients, and we factor out the 2, and we get 2 times 136, which some of you may start to see the pattern. I won't give it away yet. But now we can see that if we take the derivative of 1 over 1 minus t squared, we get 2 over 1 minus t cubed. And so, again, that's true for the absolute value of t less than 1. And then, do we see the relationship now? So hopefully you can see that x double prime is twice x cubed, which is pretty neat, right? So then what do? We now know that if we cube the first foundation polynomial, the geometric series, we now get this new polynomial, one whose coefficients are 1, 3, 6. And then we could do one more derivative just to make sure that we're seeing what the pattern is. And we can see what the coefficients are there. And if we factor out 3 factorial, we get 1, 4, 10. And then the derivative is 3 factorial over 1 minus t to the 4th. And again, we have to make sure the absolute value of t is less than 1. But now we have x up triple prime is 3 factorial x to the 4th. And so if we raise that first polynomial to the 4th power, we get the coefficients 1, 4, 10. So I'll do what Ryan did. I'll have you look at this for a little bit and tell me, see if you can see what the pattern is there, and then we'll look at the pattern together. So don't blurt it out, just look at it and see if you see what it is, and then we'll kind of work with it together. So let's look at what Pascal set tells us about what we just did in Excel. So I'm going to pull up an Excel spreadsheet, and I'm going to write down our, can everybody see my Excel spreadsheet?
Yep.
So what was our first coefficients? Kind of boring, right? That was X. And now I'm going to write down the next ones. 1, 2, 3, 4, 5, 6, right? And then I'll go write the next ones. 1, right? What's the next one going to be? 3, does everybody remember? 6, and then 10. And we could do one more, 15. And then I'll go the next one, 1, 4, 10, and we can do one more, which is 20, okay? And let's go across. Remember, this one was X prime. The next one was X double prime over 2. And the next one was X triple prime over 3 factorial. And then remember, this one was also X squared. This one was X cubed. And this one was X to the 4th. So that's what we saw in the last sheet. Does anybody know what this triangle right here is called? Does anybody remember Pascal's triangle? So this is Pascal's triangle. So by differentiating the geometric series and writing down the coefficients as we keep differentiating, we actually build Pascal's triangle. And we can see that Pascal's triangle gives us the Taylor series for E. This is the Taylor series for E right here. And it also gives us the geometric series x, x cubed, x to the 4th, and so on. So that's pretty neat that in this Pascal triangle, we see this. And then you may have seen this before, but if you haven't, this is actually pretty cool too. So if you look at nature and you look at things like pine cones and sunflowers and seashells and stuff, and you start counting the diagonals in those things, you could see in nature this pattern occurring as you count those numbers. And I'll do a couple more here. Does anybody see what happens when you look at the numbers along the diagonals I'm drawing? Are we there?
Yeah. Fibonacci.
Can we see it now? So if you add the first spiral, you get a 1. You add the numbers on the second spiral, you get a 1. The next one, you get a 2. 1 and 2 is 3. 1, 3, and 1 is 5. 1, 4, and 3 is 8. So do we see that when we count along the diagonals? 1, 1, 2, 3, 5, and 8, and so on. Do we know what those numbers are?
The Fibonacci sequence.
Those are the Fibonacci numbers. Isn't that pretty amazing? So we could see that. Oh, so somebody said the sum is Fibonacci. Great. Okay. So let's go back and to our slideshow. And so, yeah, so we saw the Fibonacci and we see that sequence 1, 1, 2, 3, 5, 8. And if we write down that polynomial with those coefficients, we get that. And so there's the polynomial associated with the Fibonacci sequence. If we multiply it by t, basically we're just shifting everything over 1. And so we get the same sequence, but it starts with a 0. And so we get that. If we multiply by t again, we're going to add another 0, and we get the same sequence with 2 zeros. So what's cool about that? Well, here's the kicker. Can anybody see Ryan's equation? So Ryan, do you see what we can do now to get your equation?
I'm looking at it. Let's see.
1 minus t minus.
Yeah, minus.
Remember the formula you had was 1.
Right. So if you divide
0.
everything by t squared, but you get more terms though here, don't you?
Yeah, but if I subtract them, if I take f minus tf minus
Oh, okay.
I have tf squared, that should be t squared f. Sorry, that's a typo. It should be t squared f. Then the only coefficient I get on this side, Ryan, is exactly what you got, was just the 1, right?
I see it. Yeah.
And then if I look at when that's 0, I get your number, the golden ratio, right? 1 over it, which was the number you had, 1 minus the square root of 5. And so if I divide, I get that thing that you had, Ryan, f equals 1 minus t squared. So the Fibonacci sequence is this rational function for t less than the golden ratio number, which is pretty neat that this occurs in nature in such a way. So if I take the derivative of that function, I get that, which is just 1 minus 2t times f squared. And if I break that up, I get f squared minus 2t times f squared. So the Fibonacci function satisfies that differential equation right there, and I can generate the coefficients for the solution to that differential equation by just writing out the Fibonacci sequence. Does everybody see that? All right, so let me show you a tiny thing in Maple just to, oops, yeah, I have a little bit of time, right? Let me show you a tiny thing in Maple just to show you the power of this stuff and what we can do. So can everybody see my Maple worksheet?
Yep.
Yep.
Okay. So I'm going to generate the Fibonacci sequence, and I'm going to pick any starting value for the first Fibonacci number and any value for the second Fibonacci number. And I'm going to hit return, and just so you can see. So when I generate the coefficients for the polynomial using that sequence, the Fibonacci sequence, notice what I see: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So I can see the Fibonacci numbers spiraling through the coefficients. And again, remember, these guys can be gotten from a differential equation. So let's look at a general one. Let's say we just pick any starting thing and we make it look like the Fibonacci, where it depends on the current one and the previous one with any numbers, capital B and capital A. And I generate it, and you're going to say, wow, Professor Sochacki, that doesn't look like any pattern in nature at all. But we're going to see some magic take place because of computers. So now I'm going to look at the Fibonacci polynomial where I put an arbitrary B and an arbitrary A, and I'm going to generate that one, and you're going to say it still doesn't look like anything. So now I'm going to have the magic of computers. I'm going to have it print the polynomial and the coefficients by sorting in B's, and let's see what happens. So here's the one from the polynomial is the first one over here. And after the asterisk, the quotation marks, the second one is the coefficients generated by my recursion formula, and they should both be related to the differential equation. But you might see that, say, there's not really symmetry here. If I look at these two, yeah, they kind of start the same, but then they get different a lot. So let's go back, and I'm going to change the P0 here to a 0. And I'm going to go through the same thing. And you're going to say, well, it still doesn't look nice, but now look what happens. B squared, B cubed, so I get all ones. Then I get the counting numbers, 1, 2, 3, 4, 5, 6, 7. Then the next numbers, 1, 3, 6, 10. And if I look at the rows, they're both the same. So I have the symmetry on both sides. So the polynomial, the power series, and the recursion formula for the coefficients give me the same thing. And if I pick B equals to A and expand it, it's pretty easy to see that I get the symmetry, and the polynomial and the recursion formula give me the same coefficients. So I can get the solutions to these differential equations by doing that. And if you have never had your students do this or do that yourself, if you multiply out the powers of 11, you see that we also get the Fibonacci, the Pascal triangle, and we can see that it matches the coefficients that we got up here. And just to show you that everything I did was right, let's pick A to be 1. And if I pick A to be 1, I most certainly should get the thing that Ryan showed us. I should get the Fibonacci sequence. And I see I get that 1, 2, 3, 5, 8, 13, 21, and 34. So this is pretty neat that the Pascal triangle and the Fibonacci sequence are so related, and that they give us so much in differential equations. So one last thing to show you. If I write out any sequence, I can go backwards the other way. I can subtract the initial condition and divide by t, and I get a new polynomial. And if you look at doing this with e to the t, sine t, and cosine square root of t, you'll find out that you get lots of famous biological and chemical reactions, which is pretty cool. So if you take this model, x prime equals x to the r, which describes lots and lots of biological and chemical processes, and you write it as x times x to the r minus 1, and you let y be x to the r minus 1, and you take y prime, you get standard calculus, right? And then you replace x prime from the equation above, and what you find out is that y prime is something times y squared, which was our foundational differential equation that is in the Pascal's triangle and is also related to the derivative of the Fibonacci function. So we can see that nature, which has this differential equation in it in so many places, is inside the Pascal triangle and the Fibonacci sequence, which is pretty amazing. And if you want to go one more, I'll just go quickly because we're out of time and it's Friday and you all want to go do other things, but you could do the same thing here. You can do, if you have two exponents, like a population dynamics problem with a p and a p squared for the population, then you can do two substitutions and do the same thing, take the derivatives, work it out. You have an x to the minus 1, but we learned before that if you take that derivative, it's the same as squaring. And so all these logistic population problems can also be written as Fibonacci and Pascal recursion relations, and you can solve those. Okay, thanks for hanging with me. I hope you guys enjoyed that.
Thanks, James.
Yeah, thank you, James.
That was
It's an
awesome.
incredible amount of beautiful structure.